Um, Hi, in this video, I'm going to talk about the solution for the problem search in rotated sorted array. Let's look at the description. Suppose a sorted array is rotated at some pivot unknown to you beforehand. For example, 0, 1, 2, 4, 5, 6, 7 might become a 4, 5, 6, 7, 0, 1, 2 if rotated. In this case, it rotated 4 steps to the right. You are given a target value to search. If found in the array, return its index, otherwise return -1. You may assume no duplicate exists in the array. Here are two examples. For this array, if our target is 1, 1 is at the position 2, so we return the 2. If our target is 0, 0 is not in the array, so we return the -1. Thinking of the solutions, the most straightforward way is just loop through the array and compare each value of the element in the array with the target. If there is a match, we return the index. If there is no match after the looping completed, we return -1. The time complexity of this method is big O(n), linear time. If we look at the features of array, it is sorted, it is rotated, there is no duplicate in the array. So we might can think there might be a better solutions than the time complexity of a big O(n). Generally, for sorted array, we usually use a binary search to find our target number. In this case, let's check if our binary search can fit into these problems or not. Okay, let's take an example. 0, 1, 2, 4, 5, 6, 7. This is the sorted array, and it is unrotated. After rotating, let's suppose that the array after rotating is A. So there are two possible situations for A. First, after rotating, the order doesn't change, which means after rotating, this is our original array, and A will becomes the same order. That might happen when the rotated step is 0, or the length of A, or the multiples of the length of A. So the element will come to the same position after rotating. So the trend, you can draw a simple diagram here. The trend is like this. And the second situation, after rotating, the order has been changed. So, for example, if we rotate this array to the left for 3 steps, after rotating, 5, 6, 7 will be rotated to the front, and 0, 1, 2, 4 will be rotated to the end. So if with a simple drawing, we will find the trend is like this. Yeah, which means we have two ascending subarrays in this array. Let's check if we can find our target with a binary search. For situation 1, of course we can use it. This is just a solely ascending array. So this is just an array in solely ascending order. The concept of binary search is to define a search window with a left and a right index. What we are going to do is for each round we find the middle value and the middle index and compare it with the target. If the target belongs to either side of the middle value, then we will remove the other side of the search window. For example, if the target is smaller than the middle value, the value at the middle, which means the target is falls onto the left side, then we can remove the right side of our search window and reduce the size of our search window to the half. So we move the right to the mid, so the next round we can get the middle value of our new search window and compare it with the target until we find the target or we couldn't find anything, we return -1. But in the second situation, we have two ascending subarrays. We might need to do the evaluation on each subarray. So let's write a binary search. So we have a left, right index to define our search window at the beginning. Left and the right are at the beginning and the end. So left plus 1 is smaller than right. So when left and the right is neighboring with each other, we stopped the while loop so that our final value will either be on the left or on the right, or return by the when the middle value equals target. So let's first get the index of our middle value. If the middle value equals to target, which means we find the target, we return the index, which is middle index. Then we are going to check which side the target is on compared to the mid. But mid value can be on the left side of the pivot, we call this pivot, or on the right side of the pivot. So it's easier to evaluate by the two conditions. If the middle value is on the left side, how do we know it is on the left side? So as we can say, all of the values on the left side is larger than or equal to a left, which is this value, and all of the values on the right side is smaller than or equal to the a right. So we can make use of this if a middle value is larger or equal to a left. Alright, we got the range of our middle value. Then we can check which side our target is and remove the other side of the search window. For example, if the target is on the left side of the middle value, which is and somewhere on this line, it will be on the left side of the middle value. Otherwise, if a target is somewhere at this, has a value that fall into this range, it is on the right side of the middle index, so that we can say if we can write our condition if it is on the red line, it is on the left side of the middle value, so the range of the red line is larger or equal to a left. Not equal because we have checked equal and this. So if target is between a left and a mid, alright, it is on the right side, so we can remove the left side of the search window by simply moving the right to the mid. Else, if the target is on the on the green line, it belongs to the right side of the middle index, and so that it can simply abandon all the values that is red on the red line, so left equals mid. We narrow our search window by moving the left and the right index. Similarly, we have checked the middle on this side. If the middle is on the right side of the pivot, we do it similarly. So if it is between, the target is between a right to a middle value to the a right, it is on the right side of the middle value. Yeah, we check this range first because we can say this range we need to get 4 values, the maximum value to this one and this minimum value to the mid, but we don't know the maximum value and the minimum value. What we can do is that we check this part first and use else for the other side. So if target is larger than mid value and our target is smaller than or equal to our right value, we can cut this part off. So left value equals mid, else right value equals mid. Alright, after the while loop, either the mid value are returned if there's a match, if the a middle value equals target, or after the while loop, we still need to check if the value on the left or right side equals to the target. If it is, we return left or right. If no, we return -1. Because left and the right are neighboring with each other. When we do the middle index, when we calculate the middle index, sometimes the right value may not be included because the middle value is always usually smaller than the right index. So after the loop, we need to check both of them to make sure if target is at this 2 index or not. This code satisfies our situation 2. For situation 1, let's say if this code satisfies this case, also satisfies this case, so we get our middle value. If middle value is larger than the A left, which means larger than the A left, which means all of them. And else, we don't have else because all of the element is larger than A left. So we can then check if we have our middle value here, and then we can check if target is at this side smaller than the A mid, we write equals mid. Yeah, else left equals mid. Yeah, it fits into this scenario perfectly. The only difference is in this one, we just do both sides. In this case, the one side is empty and the other side just include every element. So it also fits into this code. Alright, that's all about this problem. It's a solution. Thank you for watching.